hope I'm properly audible and my screen is visible. So PUTH Routhz Hurwitz Hurwitz stability criteria. Stability criteria. Okay. Now, what is this Routhz Hurwitz stability criteria? It is just a technique, right? So, just technique first to understand quickly, right? Quickly whether the transfer function or the system whose transfer function we are dealing with is stable or not. Okay. So, whether system is stable or not, we are trying to understand quickly using this Routhz Hurwitz criteria. Okay. Now, what do you mean by stability? So the question is, what do you mean by stability? As we know, any system, any a small system, it may be motor or a generator or any mechanical rotating device. How can you understand it's stable or not? Stable or means we can say the output is within our limits. Whenever the output is controllable within the design limit or desired limit by the customer or the user, we can say the system is going on in stable state. Sometimes the output is beyond our control or beyond our observable uh, limits. We call system is going to be unstable, right? For example, I have a motor. For example, I'm just giving an example of a motor. So I have a motor. Its rpm is desired rpm is around say 1000 rpm, right? But when I operate it, when I give some power supply, when I give some power supply plus minus whatever, it is rotating at a very high speed, right? In such a very high speed that I'm not able to control it, right? It is going around 5000 rpm and it is increasing 5000, 6000, 8000, going on like this. Okay, so whenever the system, here the system is a motor system which I'm giving some input, it is going beyond my required limit or the design limit to 5000, 10,000, 12,000 again coming us without anyone. So I call the system is unstable. So if in a graphical way, if you represent, you have a system. You're plotting the output of the system, right? This is a V output or output, not voltage. It can be output. So this is a time. I can say this is the time, fine. So when I plot the output of the system, what I'm getting, system is beyond my control, is going beyond my control, something like this. Okay, so this is a typical example. Another example may be using a sine wave. If I'm using a sine wave, it will be like this, rotating is going. So this is, you can see the output is beyond our control. It is increasing exponentially, right? So this is I call a system is unstable, right? So again define, we are designing a system. We know when we design a system, we know the output should be within this limit, rpm should be this much, or voltage range should be plus or minus something like this, right? So it's a stable system. You can say, you know, what is going to be the output of a stable system. For example, here I'm plotting the output of a stable system may be starting from zero, it may increase, it may decrease, or something like this. This is a stable system. We know the output is within the limits. Or sometimes you can better access starting from a particular value, starting a particular value, it is going on decreasing. Here I'm able to perceive what is the output after some time t or in time infinity, in a steady state. This in a steady state, and the output is under the specific limits which are desired, right? As the time goes on, right? So another example can be like this. Say it's starting from some point here and we're going to reach here. So here also system is stable because it is output is bounded between the desired by the user. Okay, so this is the stable system. So these are three examples of stable system. So another example of stable system is sine wave. I will give you an example of sine wave stable system. So this is sine wave, although it is continuing and is going on decreasing. So this is can be considered stable system because you can see the amplitude is going on decreasing. So I can, although I cannot predict the exact output of this sine wave, but it is still within the bounded limits. You can see the amplitude is decreasing. So this is also stable. So what about unstable system? In unstable system, we can say it is beyond our control. It is going like exponential way, something like this, going in exponential way, right? Or negative exponential. We cannot uh, predict or perceive what is going, or we can have sine wave is going in exponentially. right? This is also not in our control. Okay, so that's about the stability. So whenever the output is not in our control, which can be current, voltage, or output is up to us. What is we are trying to deal with? Can sometimes it may be power, sometimes it may output wattage, sometimes maybe voltage converter. So all those things, when they go out of control, we say the system is going to be unstable system. Now, how to understand whether the system is going to be stable or unstable? So one thing we have studied is, uh, any system we have a transfer function, right? So any system we have designed, for example, we have motor. Can take an example of motor, right? So this is a motor. At least you should imagine this is a motor. Okay, so I have an input. We can give input motor. So if I have a transfer function of this motor, say for example, a square plus 1 divided by 2, 2s plus 4, something like this. This is the transfer function of this motor, right? So here we can see two things. Here there is a denominator, no, numerator transfer function in terms of Laplace transform, and the denominator ds, right? So there are two transfer function. One is ns, one is ds, and this I call as hs, right? You remember, this is can be standard. You can call as hs. So hs is a transfer function of this motor or this dc motor or whatever, called hs in terms of transfer function as Laplace transform as parameter. Now, we have divided into ns and ds, right? So this ds is called the characteristic equation. This ds is called the characteristic equation. C characteristic equation. So this equation or this C or denominator forms a very important part in understanding the stability of a system. So usually before going fluent, we should understand that one rule of thumb. One rule of thumb we already studied is whenever in the S-plane, whenever the root of the characteristic equations lies in the right side of the S-plane. This is S-plane, okay? This is S-plane. This is S-plane. We have negative. This is negative. This is positive. So whenever the roots of the characteristic equation, here we are talking about the denominator. So we have an ns numerator and denominator ds, right, of the transfer function hs, right? Here ds is called as the characteristic equation. So when we plot the characteristic equation, root of the characteristic equation in the s-plane, if the roots lie on the right side of the s-plane, so what we call these roots, we call this are nothing but poles, right? So if the poles are plotted or poles are located in the right hand side of the s-plane, we call that system is unstable. This is one way we usually do, right? Quick way. But if the poles remain on the left axis or left side of the origin, we call that system tends to be stable. So that from that we should understand that if the roots remain on the right side of the S plane, so that means what is the meaning of that? For example, so that means we have unstable system like this. Your output is going to be bounded. This is the time transient response I'm showing you. Unbounded. Your output is going beyond the limit. So right, something like this, or it is increasing like this, something like this. Now let us move a bit more closely. So what is the meaning of when we say the roots will remain on the left side? Say for example, we can take a simple example: 1 divided by s plus 1. So this is a simple hs transfer function where the denominator ds, we can say ds. What is ds here? The ds denominator equation is s plus 1. So what is the root of denominator here? So the characteristic equation, this is itself is the characteristic equation. So this is the characteristic equation, ce. Okay, so what are the root of the characteristic equations? Here we know the root is s equal to minus 1, right? So s equal to minus 1 will be plotting a point s equal to minus 1. This is minus 1, right? So here the root or the poles are remaining in the left hand side of the s plane, right? Poles will be remaining here. Okay, if it is complex conjugate, we can say still it will be remaining in this axis. Maybe something here and here, complex conjugate will be remaining here and here. Plus j, this will be plus j, this is minus j, something like that. Okay, still in these cases this is origin, so the poles are remaining in the left axis. Now we are considering the characteristic equation, this s plus 1 is the character, so s equal to minus 1. So so that is stable. You can say that system is stable. Now if we have a characteristic equation something like this, s minus 2 equal to 0, if the hs is s 1 by s minus 2, this is the hs. So from that we'll take the characteristic equation s minus 2 equal to, so here s equal to 2. Now here we can see the root is something like s equal to 2 will be lying here. Okay, so either here or it will be conjugate like plus or minus 2. So here in this case we can see the poles are remaining on the right hand side of the origin in the s plane, so the system is going to be unstable, right? So the output, if you plot the transient response, will be dynamically increasing or dynamically decreasing or actually fluctuating, can also be fluctuating. This is complex conjugate, we'll see a fluctuating output, right? So we'll discuss this more deeply, but let us now discuss, instead of plotting, sometimes we have very complicated uh, hs. For example, here this the hs is something like this: 1 plus 2s plus 4s squared, and we have 4s raised to 4 plus 3x cube plus 2s plus 5, etc. So we cannot perceive right immediately whether the poles, where is the poles located, because there are around 4 roots here. You can see there are 4 roots. Why 4 roots? Because s to the power 4. So we have four solutions to this characteristic equation. Which is the characteristic equation? This is your characteristic equation, denominator equation, ds, right? Now we cannot immediately perceive where are the roots lying. So it's very difficult. Once we want to solve it. So what is the way of solving? We'll discuss that also. I think we have to solve it into this one: a by s plus a plus b by. So we'll solve it like this. But we will make it simple equations, and then it takes time. So okay, so but like if I don't want to take spend so much time, I need an automation system to tell me whether the system is stable or not. Say I need to program a computer so that the computer can immediately see the equation and tell me, instead of going for solving all the complex and all the uh, complicated methods. So then we go for the Routhz Hurwitz criteria, right? Now let's see why we are using Routhz Hurwitz criteria later. Basically, we are analyzing whether the poles are remaining on the right side or left side, or how many poles are on the left side or how many poles are on the right side, basically. So we are determining whether system is stable or not by regressing, or we are speculating, or we are we can say we are predicting how many poles are on the right side. So that is what Routhz criteria telling us. Okay, let's jump to the Routhz criteria. Now, RH criteria tells you, so to apply Routhz Hurwitz criteria, first you will be given a transfer function. For example, I'll give you an example. Mm, Say we have a transfer function h of s, or standard 1 by s square s raised to n. Maybe I'll give you some coefficient also: a raised to n, s raised to n, a raised to n minus 1, s raised to n minus 1, etc., till the constant I can see a0, right? So this is my standard, some not standard, some transfer function where my characteristic equation is, I'm using the characteristic equation here. See, characteristic equation is nothing but an s raised to n, and goes on like this. A raised to coefficients are an minus 1, and the variable s variables are going like this. Okay, till I have a1 s raised to 1 plus uh, a0 s raised to 0. That is, this is the characteristic equation, right? So we are given a characteristic equation. Now you should use the Routhz Hurwitz criteria in order to determine whether this characteristic equation is stable, or if there are any roots on the right side of this plane, or If there are roots, how many roots are there? That's it. Right. So first step is, yeah, I think better to take an example instead of mm, writing like this. So, or I can just simplify and write something according to this equation. So I'll just write the equation again here. We have characteristic equation. Okay, see equation in terms of S. So a n s raised to n plus a n minus 1 s raised to n minus 1 goes on till a0 s raised to 0. Okay, so this is my characteristic equation. Now I'm going to draw the Routh array. What am I going to do? I'm going to try the Routh array. Draw the Routh array. Routh array. So what is Routh array? Right. So we'll start with 2. Start drawing a straight line. Now from here we'll start all the coefficients we require. First we need to start from s raised to n, then s raised to n minus 1, then goes on s raised to n minus 2 till s raised to 0, s raised to 0, right? So this is, we are writing outside the array. Now we are going to write a lot of things inside the array. So let's see what we are writing. Now the first thing we need to take is the first thing, an. We need to catch the an. Now we're going to write an inside the array. So first thing corresponds to straight line of s raised to n. We are going to write straight to Sn. So I'm going to write a to the substitute n. So an I am written. Now let's go to second, a to the n minus 1. That I'll write below. The an. Right. So I'll be writing a to the n minus 1 below the first what I have written. Now what I'm going, now I'm just going to crisscross. Now I'm crossing. Now I'm the crossing. Now the a raised to n minus 2, I'm going to write here a to the n minus 2. Right. Again I have to go bottom. Again I need to go bottom and to write a n minus 3. A n minus 3. Okay. So I've gone writing like this, till I reach the a0. Okay. Now again I will go to crisscross. So the first two rows, I'm writing the first two rows only. But it goes on like this. A n minus 4 and then a n minus 5, go on like this till I'll reach a0 here. A0. Right. Once I reach a0, I can make a 0 in the last part of last column, second row. Okay. It's up to, if sometimes there is no required for that 0, but sometimes we have to give. Sometimes the a0 is coming in the bottom, like here we don't need to put that 0. We can immediately put a0 here, right? Then we can close our Routh array. We completed our first two rows. Okay. Now what I have taken, I've taken the coefficients of s from my characteristic equations and just placed inside the Routh array. You can note that I've just placed in first two rows only. Okay. Now how to fill the Routh array in the third row? Now you should know this. There is simple equation, or what I'm trying to do is I'm just multiplying the bottom to top. I'm going bottom to top. You can see here I'm bottom to top. Okay, an minus 1 into an minus 2. Okay, then what I'm doing, I'm then minus into minus of that into an into an minus 3 divided by an minus 2, something like this. I'm just going a crisscrossing and multiplication. I'm just writing. So what I'm trying to do is this we are trying to, now I'm going to find the value of b1. Now what is the b1? I'm writing the equation b1 here. b1 equal to here a n minus 3, sorry, bn equal to a n minus 1, a n minus 1, and top, we are starting from bottom then going to top, into a n minus 2, right? A n minus 2, right? Now minus this minus, now start from the a n into a n minus 3. Again we are coming from the top to the bottom as multiplication, and whole divided by a n minus 1. Yeah, I think this is what I'm doing. Again I'll repeat what I have done. I start from the bottom, a n minus 1. Now I'm going to top an minus 1 into an minus 2, right? From that, that's a single term, then minus, then I took an into an minus 3, right? Again, this whole thing divided by an minus 1, right? I'll just reduce the thickness of my pen, thus I can write much better way. Okay, so I'll again write. So okay, so what I'm going to write is b1 b okay, b1 equal to, what is b1? b1 equal to, first I'll take the bottom, that is an minus 1 into an minus 2, n minus 2 straight to top, minus an into n minus 3, n minus 3, right? Divide by an minus 1 again, right? So this is the equation. You can note that an minus 1 is coming two times. It's starting from a minus 1 and ending from an minus 1, right? So this is b1. Now what is b2? Now let's see what is b2. b2 b2 also start from where? Start from an minus 1 only. Now we can see we are going like this, an minus 1, we are going to an minus 4, right? An minus 4 again, minus minus n into, like this, n0, here it's a0. So what I done, again divide by an minus 1. So let me start with an minus 1 only. Again I'm starting here also with n minus 1, multiply with n minus 4, bottom to top, so remember that, multiplied, sorry, this I multiply now, minus what, minus again an into a0, here it is a0, right? So divide by, again same, an minus 1 only, right? So here again I'm going to crisscrossing. So you can see I'm starting from an minus 1 going to an minus 4, that is we are trying to find b2. So we are taking the column right of b2, right? We are taking the column right of b2. So starting from an minus 1 going to an minus 4, right? Then minus again an into a0 here, although it can be n minus 5, but I'm just taking an example here. Okay, okay, so likewise we calculate all the rows. Now we can calculate b3 also. Here in this example b3 is 0 because now there is no other option after this thing. So this goes to here, there's no 0 value here, again minus this into again 0 value here. So b3 is, in this example, is 0 only. And again we complete all this rows till we reach the s raised to 0. Now till we reach the s to the power 0 of the Routh array. Now what we'll write in the s to power 0? That is the value a0, the last point of a0. We have to write a0 here, a0, that's the last element in this row, a0. Okay, so we'll fill all these elements in the Routh array following this principle, right? Now we'll take an example so that we can understand much better. Now let me tell you the conclusion also, what we are trying to do in Routh stability criteria. What we are going to check is, we are going to check the first column of the Routh array. First column of the Routh array will check all the individual elements, all the individual elements, all these individual elements. If the all the elements are having the same sign, that means the system is stable, right? If the all elements having the same sign, then that means the system is stable in the first column of the Routh array. If there is any single sign change, that means the system is unstable and there is exactly one root in the right hand side of the S plane, right? If there is one sign change, for example, or one sign change, how it can happen, all are positive, all are positive, all are positive, last element is negative. That means how many sign change? Only one sign change. That means only one root remains in the right hand side of the S plane. Another example is, first is plus, then all are minus. So there is also one sign change. And there is first is minus, then all are positive. So in these cases, we know there is a sign change, but there is only one sign change. So there is only one root on the right side of the S plane, and definitely the system is unstable, right? Now, what happens if there are two sign change? Two sign change also that means the system is unstable, and there are now two roots on the right hand side of the S plane, right? So this is what we are going to check. For a system to stable, it is necessary and sufficient that each term of the first column, that is first column, each term of the first column of the root array, and it should be same sign, or you can say it should be positive. If you have taken the a raised to n is positive, all these elements should be positive, right? If an is negative, all the elements should be negative. So we can say there should not be any sign change, right? If this is not met, if this condition is not met, we can say the system is unstable, right? And the number of sign changes in the first column corresponds to the number of characteristic equation, or number of roots of the characteristic equation in the right of the S plane. Okay, so we are focused on the first column of the S plane. There should not be any sign change for a stable system, and as many number of sign changes are there, it means that many number of roots are there on the right side of the S plane. For example, we have some examples like, for example, we have something like this: plus, 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 minus, plus. So how many sign changes are there? Again, there are two sign changes, right? So one sign change is here, another is here. So there are two roots on the right hand side of the S plane, right? Now we'll take an example that will be more clear. Okay, so although this is a bit of theory, so we'll just take an example. Okay, so we are given a characteristic equation. This is the characteristic equation: s raised to 4 cs. I'm giving cs. S raised to 4 plus 8 s cube plus 18 s square plus 16s plus 5. Okay, so first we should check all these are in correct order. S after 4 we have 3, s cube, s square, s raised to 1, and s raised to 0. So they are in order. We don't need to fill it with any zero coefficients because they are in order. Now first we need to draw the root array. Okay, so root array. This I'm going to start the root array here. So let's see. This is s raised to 4 element, s raised to 3 element, s raised to 2, s raised to 1, and s raised to 0. Right. This is just for noting the rows, different rows I'm going to get here. This is the first row, second row, third row, fourth row, and fifth row. That's it. Now, how to start? You have to start with the coefficient of the s raised to 4. This is 1, right? And this is the 1. So, coefficient of s raised to 4. So, we start with 1. We should write 1 word. Yes, here. First element a raised to n, right here. Now, the second element is 8, right? It's coming to 8. So, 8 should be in the second row. 8. Now what is third element? 18. So 18 again comes to the here zigzag. It should go zigzag. Now 18 has to come here. So I'm going to 18 here. Right? Now again you have to come to bottom. That is 16 in the bottom. Now we have 5, right? We have 5. Now this 5 is the last element, and so we don't have any of them, so we have to write a 0 here. So this completes my first two rows. Okay? First two rows of my root array. Now, how to find the element? How to find the element which I need to write here, the star. Let it be star. So, what is the principle we have studied? First, start with the bottom 8, then go to top 8 into 18, 8 into 18 minus 1 into 16, right? So, I can write like this. In place of this, I should write 8, 8 into 18 minus 1 into 16 divided by 8. That is the starting element, right? So I just again I'll repeat, start from bottom 8 into 18, then 18 minus 1 into 16 again divided by 8, right? So this is we are, you just remember this thing: bottom to top, again to the left with the minus, and then come back and divide by the first element. Exact. Okay. So this is our B1 element. So what is 8 into 18? Um, so what is the answer of this? 8 into 18 minus 1 into 16 divided by 8. So here 8 is common. So you can say 8 is common here. I'll take 8 outside. Here then you have 2 here, 2 here, right? So okay, so 8 and 8 cancels. So 16 minus 18 minus 2. That's nothing but 16. So this is nothing but 16. So I'll replace this with the 16. So we call 16. So it's first is 16. Okay, now what is the second B2 element? Again the same thing. I will start with the bottom 8. Again I should go to the 5. 8 into 5 minus 1 into 0 divided by 8. That is nothing but 8 into 5. 8 into 5 minus 1 into 0 divided by 8. So you can say here it is 8, 8 cancels, so it is nothing but 5. So I'll get a 5 here. So this is a 5. I'll get a 5 here, right? Now, what is the next element? We know next element we can see that if I'm product 8 into here is going outside, right? Because we need to take the column right side of this present value we are finding. Right side this is 0. So here is 0. 8 into 0 minus 1 into again 0. So nothing but we'll get a 0 here, right? And what about the next element? Next element is S raised to 1. Again, now we need to do the same process. We need to do the same process in next row also. Right now, what is the element? Answer. Right now will be 16. Start with 16 into 16, right? 16 into 16 minus 8 into 5. 8 into 5 divided by 16. This is the first element of the S1 row. So here you can say if you take 16 common, take 16 common outside. Here we'll have 1 by 2. Here 1 by 2 will be here. Close it. So 16 cancels. 16 minus 2.5. Right? 16 minus 2.5 is 13.5. So we got the 13.5 here. So we got 13.5 here. Okay, now again the process continues. Now what to do? Next is 16 into 0 minus 8 into 0 divided by 16. 16, so that is nothing but 0. You know that is nothing but 0 only. So again here it is 0. And again this element is going to 0 only because again 16 and this 0 minus 18 with this 0. That is also 0. Now you need to find the last element. You don't need to find the last element because S0 we should take the A0. This will come here. That means 5 has to come here. Okay, and rest other elements again 0 0. Fine. So now we can see what is the first row comprising of. You can see first row is comprising of 1 8. This is 8 1 8, then 16 is there, and 13.5 and 5. So all these elements are positive. So there is no sign change. So we can say the system we were discussing or system we are concerning characteristic equation s raised to 4 s raised to cube 8 18 square is a stable system. There is no holes on the right side of the s plane. Okay, so this is the mechanism, right? Fine. So this is we have already found this system is stable. Now let's take an example of another system. Okay, so now the CE carry equation in this system. Any doubts you can ask? I think the at least the procedure is clear. Say this is 3s raised to 4 plus 10 s cube plus 5s square plus 5s plus 2 plus 2 equal to 0. Now we have to check whether this is a stable system or not. Okay, so first we'll write the gas equation. This is our array, Routh array. So start from s raised to 4, s raised to 4, s raised to 3, s raised to 2, s raised to 1, s raised to 0. One thing we know, what we know that corresponding to s raised to 0 is the last element 2. So immediately I can write 2 here, no doubt, right? So that 2 is coming here. Now s raised to 4, these are the rows. So I'm just, this one is first row, second row, third row, fourth row, this is the fifth row. Now first element is definitely going to be 3. This 3 is going to be first. 3. Now 10. 10 is going to the bottom. We should know the coefficient. S raised to 4, they are in order. S raised to the power 4, then 3, then 2, then 1, then 0. Right? They are in order. So I can write that 3, 10. Now zigzag. I have to start from the first row again. Right? Then 10 ke baad 5. Again next is 5 again. Again we have 2. Again after 2, so we have to fill it with 0 because there's no element. Right? So we have completed the first 2 rows. Now we need to find the value of B1 here. B1. Say this is B1. After A's rows, we have B's. So what is the equation of B1? Again, I repeat, B1 equation is um, you should just identify this path. Lower element, then top minus this into this divided by lower. This exact equation, right? Again, I'll repeat, start from the bottom 10, go top into, it's a multiplication, then minus 3 into 5 divided by 10, right? So we have 10 into 5 minus 3 into 5 divided by 10. That is 50 minus 15 divided by 10. That is 35 divided by 3.5. Right? This is 3. So we got B5 something but 3.5. 3.5. Now what about the B2? Now again start with 10. 10 into 2 minus 3 into 1 divided by 10. Right? So now we calculate B2. B2 is 10 into 2. 10 into 2 minus 3 into 1 divided by 10. That is 20 minus 3 divided by 10. That is 20 by 17. 1.7. We got 1.7 here. Is there any wrong here? 10 into 2 minus 3 into, okay, 0. That is not 1. That is 0. Okay. This is actually 0. So you should know that I wrongly written here as some complicated signal. So 0. This is 0. 3 into 0. Right? So 20 minus 0 divided by 10. That is nothing but 2. 20 minus 0 by 10 is nothing but 2. So this is not 1.7. This is 2. Okay. Last element. Last element, how you calculate? 10 into will go outside. Outside. Why? Because this element where we need to find, I have to take the diagonal row or column. So here it is nothing but 0 0. So this element is answer should be, this is nothing but 0 only. So this is 0. Okay. Now what about this C? V ke baad C. So C1, C2, C3 row. So what's the value of C1, C2, C3? Same thing, same procedure will continue. Now what the value of C1 is? C1 is nothing but 3.5 into 5 minus 10 into 2 divided by 3.5. So here we can see 3.5 into 5 is I think 17.5 minus 20, that is minus 2.5 divided by 3.5, that is 25 by 35. 25 by 35, 5 by 7 something. So but it should know it's negative. It's negative 5 by 7, minus 5 by 7. Right, so this is a negative value coming, so we should know that now that we understood the system is going to be unstable. Right, but we can calculate C2 also. So what is C2 here? Now C2 will start with same 3.5 here, 3.5 into 0 minus this into 0. So 0 minus 0 divided by 3.5. Right, this is nothing but again 0. Right, again last element, this into this into this. Again this will be 0. Right, so this is our um, first row. Now we focus on the first row. Now how many sign changes are there? We can see there are positive, 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 negative, and then a positive. So how many sign changes? There's two sign changes. One here and another here. Two sign changes. So there are two roots on the right side of the S-plane and two poles. So there are two poles on the right side of the S-plane, and system is unstable by Routhz Hurwitz criteria. System is unstable as it has two poles on the right side of the S-plane. Right? So at least I think we can practice with some questions. Um, Now there are some cases where we need to do some additional things. Special cases are there when the all elements of a row becomes zero, something like that. And we have two options. Mm, so and sometimes we have to check. Say for example, I'll give you an example. So I'll give you an example. You can try that. So the characteristic equation is characteristic equation. For example, I have s raised to 3 s raised to 4 plus 4s cube plus 5s squared plus 6 plus 6s plus 7. So now try to find whether this system is stable or not. So I'm just randomly put some coefficients 3, 4, 5, 6, and 7. First, you should check whether they are in the powers of s. S raised to 4, s raised to 3, s raised to 2, s raised to 1, and s raised to 0. Right? Now we can start the procedures. Please try it and tell me whether the system is stable or not. So what is the first step? Yeah, we should start with the row. Start with s raised to 4, s raised to 3, s raised to 2, s raised to 1, s raised to 0. These are my possible rows. First row, second row, third row, fourth row, fifth row. Right? Now just put everything in order. So 3, 4, again zigzag. 5, 6, again 7, then 0. Right? Let me close the root array. This is the root array. I'm closing the root array. Now, what is this element? B1, B1, B2, B3. We are going to find, and then C1, C2. There are two poles in the right side. I can show saying. Let's see. Right, and this last element we know definitely it is going to be 7. This is 7. This is 7. So anyone is getting it is unstable. So now uh, let's see. So what is B1? So B1 is nothing but 4 into 5 minus 3 into 6 divided by 5. So 20 minus 18. 20 minus 18. 20 minus 18 divided by 5. That is 2 by 5. Yes, B1 is 2 by 5. Now what about B2? B2 is 4 into 7 minus 3 into 0 divided by 4. That is nothing but 4 into 7 divided by 4, 7. Right? Last element definitely we know is 0. Now what about C1? C1 is 2 by 5 into 6. So we know C1 we are trying to go here 2 by 5 into 6 minus 4 into 7 divided by 2 by 5. So this is B. So this is C1. We are trying to go C1. That is 2 by 5 into 6 minus 4 into 7 divided by 2 by 5. So we can see there is a negative, right? Here 2 by 5 into 6 is 12 by 5, very small value, around 2 point something. Minus 28 is here, so it is a negative value. So we have a negative C1 value here. So right now we can conclude that there are two change of signs, right? Here plus, 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 negative, and plus. There are two change of signs. What are the two change of signs? One is from here, negative, again negative to positive. So two change of signs. So we can say there are two poles on the right hand side of the X. Okay. Okay. So this is the Routhz Hurwitz criteria. Two special cases we'll discuss maybe next class. Maybe I think tomorrow. If I can I take any class tomorrow? If can I take after DC? Is there any class for you? Wednesday? Okay, if there is no class, please let me know so that we can complete the rules RH criteria. Okay, so no class, so we can, I think we can continue this thing. There is two special cases I will tell you so that whatever question comes in the exam, we can try this rule service criteria. And this is asked in a lot of competitive exam where they will give an equation and you need to find. So after some practice, you can immediately see that some systems are unstable. For example, if I write a system like this, s raised to 4 plus s raised to 3 plus 5 s squared plus s minus 2, it is stable or unstable, we can immediately see that this is going to be unstable because there is a minus here. Right. So likewise, we can see a lot of things as you practice a lot, and we can see. Right. Sometimes the equation will be like this: minus s raised to 3 plus s squared plus s raised to 1 plus 2 equal to 0. Here also we know this is going to be unstable uh, because uh, because all these terms have different sign chain. Mostly, I'm not sure. I'm just guessing. So maybe it'll be something like this also. All are negative, so we don't know. If all are negative, we don't know. This is nothing but we can multiply by minus one, then all becomes positive, right? But if one term is definitely having a minus term, so we can say this is definitely going to unstable, right? Because the first term is going to be in the root first column, and this is also in the root first column, and this is also in the rows first column, right? So uh, checking these three guys, we can immediately even perceive whether it can be unstable or not stable because these are in the first column of root. Okay, so that's all for today. We'll continue tomorrow. I will tell you the timing mostly after DC class. We'll continue. Okay, so any doubts, I'll try to answer, or you can put your roll number.